I'd like to take a look at the solution of this inequality. 2x plus 1 over x plus 4 is greater than or equal to a positive 1. This example is a little more advanced or sophisticated than some examples because it's got a 1 on the right-hand side rather than a 0. When we solve rational inequalities, it's important to have 0 on one side of the inequality because our point of comparison for positive and negative numbers is that crossing point 0. So the first thing that we need to do is to subtract the 1 and get 0 on the right-hand side. Now on the left we have the fraction 2x plus 1 over x plus 4 minus the single term of 1, and we want to have these two terms combined into 1 so that we get a single rational expression. So we'll need to build the 1 up to the least common denominator of x plus 4. And when we do that, we can put both fractions together over the same denominator of x plus 4. And in the numerator, we can subtract the terms. We have 2x minus 1x is equal to x. But realize this subtraction applies also to the second term in the second fraction. And so we have positive 1, but minus 4 gives us minus 3 in the numerator. And now we have a single rational expression, which is set greater than or equal to 0. So we can look at these two factors, one in the numerator, one in the denominator, and each of these factors will have a breakpoint which we'll use to divide the number line into regions. From the factor x minus 3, we get the breakpoint that x is equal to 3, and from the factor of x plus 4, we get the breakpoint at negative 4. So now I'm going to use these two breakpoints to subdivide the number line into regions, and because there are two breakpoints, there are three regions: less than negative 4, between negative 4 and positive 3, and greater than positive 3. Next, I'll take my simplified inequality, x minus 3 divided by x plus 4, and I'm going to choose a test point in each of the three regions. Looking at the first region, where x is less than negative 4, I can choose any point that I like, but x is equal to negative 5, fits that purpose. And when I plug negative 5 into the inequality, I don't need to calculate exact numbers. What I'm mainly concerned with is the signs, because the signs will be used to determine whether I have a number which comes out positive, which would be greater than or equal to 0, or negative. So in this case, I'm going to plug in negative 5 minus 3 in the numerator is a negative number. In the denominator, negative 5 plus 4 is negative 1, and that is still a negative number, so I get two negatives. And negative divided by negative is a positive number. And that positive number, when I test it in the inequality greater than or equal to 0, that is true. We are expecting that positive numbers should be greater than or equal to 0, so I'll label that as true. Next, we move on to the second region, something between negative 4 and 3. When I can, I like to use x equals 0. That's a simple number to work with. And so in the numerator, we get 0 minus 3 is a negative 3, which is a negative number. But in the denominator, 0 plus 4 is a positive 4. Something negative divided by positive is, this time, negative. And then when we test it greater than or equal to 0, no, that's not true. It's false. The last region, we'll choose a point that's greater than 3. So if I choose, for example, x is equal to 4, I end up with 4 minus 3 is a positive 1, and 4 plus 4 is a positive 8. Positive divided by positive is going to give me some positive number, and that will be greater than or equal to 0. That is true. As you can see, the test points that I choose are really not that important. Had I chosen positive 5 in the third region instead of positive 4, I still would have gotten 5 minus 3 is positive. 5 plus 4 is also positive. And so the important feature here is that the signs are only going to change as we cross over these breakpoints, which we identified here at being positive 3 or negative 4. Now that we've shown the true regions, we want to shade those true regions. So region 1 is true, and region 3 is also true, but region 2 is false, so we will leave that blank. And the very last thing that we should do is to look at the breakpoints. So I look at this breakpoint at -4, and when I look at the inequality, it has an equal to symbol, so usually I would expect that this would give me a square bracket to include that point at -4, but we also have something happening here with the denominator, and that is that when x is equal to -4, it's a bad point. And since it's a bad point, we should not include x in the inequality. So I'm actually going to write here that x should not be equal to -4. So when we go and decide whether to put the square bracket for included point or the curved bracket for excluded point, I will make it curved, indicating that the point x is equal to -4 is not included in that interval. Next, we move on to the other breakpoint at +3. And we look again at the inequality. There's an equal to symbol, so normally we would want to put a square bracket there. And we look at also where that factor appears in the inequality. And x minus 3 is in the numerator, so it doesn't give a bad point. And therefore the point x equals 3 is included. And when I go back to my graph here, I want to show, because the point x equals 3 is included, that we will make a square bracket again to indicate that. The last thing that I need to do here is to write the solution, which I've shown on the graph, in either interval or set builder notation. And because the interval is very similar to the graph, I will use the interval notation. So our interval begins at -infinity. So we'll start at -infinity. Again, curved bracket because it's not a real number. And extending up to a -4 with a curved bracket, just as we have in the graph. That's the first interval, and then union. We take a look now at the second interval, which begins at +3, but with a square bracket on the left, indicating that the point 3 is included, extending up to +infinity. So this is our interval solution, and just to recap a couple of the highlights, when we look at the original problem, first thing we need to do is set one side of the inequality equal to 0. Second thing is to get a single rational term. And finally, once we determine our intervals, we need to test each of the breakpoints, because at the breakpoints, we will then be affected by whether this symbol is a greater than or equal to or strictly greater than. And finally, if one of those included points happens to be a bad point, we need to eliminate it from the solution, as we did here.